Hello, my name is Henriette Wirth. I am a PhD student at Charles University in Prague and a former software developer. In the last part of the course, we designed the program you see right here. However, one part we didn't talk about yet is input parameters. We do have our n-body simulator so far, but maybe we want our users to be able to change the frequency of the outputs or change the time step length or anything else. So what are the possibilities we have to get those input parameters into our program? Well, there are two main ones. One is you could simply use command line parameters, or you could make a separate input file. The advantages of using command line parameters is that it's very, very quick, and you can easily put it into a shell script and then just run multiple instances of your program one after another with slightly varying parameters. However, using an input file allows you to see all of the default parameters at once, and you can very simply copy your input file and store it with the output. So that if you go back to your experiments later, you can always see what exactly you've done. Now, if we put our input parameters into our program, we do, of course, want to store our parameters somewhere. So where would you store those parameters in the program? Well, the old way of doing it is to make a global struct for it, which would either be defined directly in front of the main function or in a separate file. However, as programs grew, that became more and more impractical. And so what people gravitated towards was that to not store all of the input parameters at one place, but to store them with the modules in which they are needed. So for example, the time step length and the output frequency that I mentioned beforehand would be stored directly with the scheduler. And that also leads towards the move to object-oriented programming. You see, if you have a class gives you the ability to group variables and functions together with one another. And the problem you face when you have very large programs and each module is supposed to store its own input variables and functions is that if you just use global variables, then you can get very easily into naming conflicts between the different parts of your program, so it doesn't even compile. Or you might accidentally have one part of the program overwrite the data of another one, which is the reason why you aren't supposed to use global variable. Class, however, can be seen as a little contained unit where you have the variables of the class accessible from within the class, but not so much from the outside, which we also call encapsulation of data. Another advantage that classes bring with them is what we call inheritance. So we already talked about the particle mover and how we could use different versions of it. We might use the forward Euler scheme, we might use the Rogokuta 4. Maybe in the future we want to add a Hermite integrator or any other kind of scheme that you might find useful. Previously, we assumed that we just replace one with the other. But what if we actually want to leave it up for the user to choose which integrator to use? In that case, we would, of course, want to create various particle movers that the user could then insert at this very place in our program up here. And what inheritance allows us is to create a base class, which is basically our blueprint, how a particle mover looks like. And then we can derive other classes from that base class, which then gives us the exact implementation of such a particle mover. And to demonstrate what that looks like, I brought you a little example. So for this example, I built a program similar to the one we just designed. Now at the top level of my project folder, you see I have a main file here, and I have a source folder here. And within the source folder, I have the different files defining my scheduler, the base class for the particle mover, and the Euler and the Rogokuta integrator. So let's have a look inside of these files. And what we can see immediately is that we use classes here and here. So we already can see we are dealing with object-oriented programming. Now, what I want us to look at first is the scheduler here. And what you will notice is that there is this init function here. This init function is what is the constructor in many other languages, and this is the function that is called as soon as we create an instance of the scheduler. In Python, we do not need to explicitly define a constructor for every class, so you will see it's missing in these classes. Then we just have a default constructor, but in this case, I actually wanted to do something with it, so I have to define it. And the scheduler is instantiated in these lines where here. I just type the name of the class and then the parameters in bracket. Speaking of parameters, you will notice that there is this argument self in all of the member functions of our classes. The self is an instant of the class itself. And the fact that we need to explicitly write it here is a consequence of classes and object-oriented programming not being originally planned for Python. Also, it has to be said that while in the function definition we have to add the self parameter, it is missing as soon as we call a function. So here you see you have these two parameters, but when I call the function, I only have the second one. This variable here is a member variable of the scheduler. So this is going to be visible to all the functions within the scheduler, but not accessible from the outside. What I do here is I simply take this input parameter, which is going to be the particle mover to use for our program, and I just store it in an internal variable, so the scheduler does have this information stored somewhere. And then this class has a member function here, which will compute a time step. And to compute a time step, I here define that I access this member variable, which contains my particle mover, and I tell the particle mover to move the particle. Now, so far for the scheduler. Now let's look at the particle mover base class and the derived class. If we want to have an abstract base class here, we need to import this library called abstract base class. And our class needs to be derived from this class, which we achieve by putting the ABC class here in brackets. Then we also have this abstract method keyword. If we define a function with this abstract method keyword, it tells Python that this is an abstract function, which means that it is not really defined here. Now we cannot instantiate classes that do contain abstract methods, which means that if we try to instantiate this class, we would get an error message. However, we can derive classes from this class and then implement a move particle function in that class, and then this derived class can be instantiated and used throughout the program. This way we make sure that everyone who wants to define their own particle mover for our program has to actually define a function called move particle. Additionally, we do have this function print blah. This is just a normal function that prints the word blah, and I put it here to show that this function will be inherited from all of the derived classes from this particle mover base without us having to implement it again and again and again. Then we have the derived classes here. So you can see here the particle mover base is in brackets here. And we implement a Euler integrator here. And in this Euler integrator, we define this move particle function that we have as abstract function up here. And we define that if this function is called, then our program is to print onto the terminal that it uses the Euler method. And I did the same for the Runge-Kutta. So the Runge-Kutta class here has also a member function called moveParticle, and this is to print that I use the Runge-Kutta method. Now, to demonstrate how to use the classes, I have the main function here. So let's see what the program actually does. Now, in the first line, I get an instant of this Euler integrator. And then I just call this print blah function from the base class, which means that now the word blah should appear on the terminal. Then I instantiate a scheduler, call it scheduler Euler, and this scheduler gets the Euler integrator as an input parameter. And it then is called to compute a step. And as we have discussed here, compute step calls the move particle function of whichever particle mover is stored here. So in this case, this would be the Euler integrator, which means that this move particle function over here would be called, and if we would get another line on our terminal called I use the Euler method. Now I did the same for the Runge-Kutta. So we create an instant of the Runge-Kutta integrator. We then print the word blah on our terminal, and then we instantiate a scheduler, this time using the Runge-Kutta integrator, and we compute a step for that scheduler, which then also will call the move particle function here. However, this time from the Runge-Kutta integrator. So we should see this line on our terminal. Okay, let's see if everything works as predicted. Well, as we predicted, we see here the word blah. I use the Euler method, blah, I use the Runge-Kutta method. And in this way, you can add whichever number of integrators you want to your program, and then just switch them out using a parameter defined by the user. With that, thank you for joining me for part 2 of this course. And if you are interested, you can join me again in part 3.